Hello to my Honors Math 1 students. Today's lesson, we're going to be focusing on two sections out of our textbook. It's section 2.12 and 2.13. So we're talking about linear equations today and expressions and things like that. And so before we begin, let's go over a few things, a few of our definitions. So a postulate or an axiom is a statement accepted as true without proof. For example, we have the addition postulate, and there's others. There's a subtraction and multiplication and division and lots of other postulates. But here's one example here. If x equals y, then x plus 4 has to equal y plus 4. A theorem, on the other hand, is a fact that follows logically from other known facts. So it's a major result that has been proven to be true using operations and facts that were already known. For example, here, angles on one side of a line always add to 180 degrees. They are supplementary. So we've got three theorems right now in this chapter 2 that we are beginning this semester in. We are not focusing on chapter 1. And there are a lot of things at the beginning of chapter 2 that I'm skipping over, but I'm going to hit them all with the lessons in the next couple of weeks. So the beginning of chapter 2 and a lot of chapter 1 is really things that you should have learned in the past. So I'm not going to focus on those. We have much more things to do this year. So here are the three theorems that if you're reading them, they should make complete sense to you. If you have some non-zero number and you're multiplying it times 0, then obviously your result, the product, is going to be 0. So a times 0 is 0 times a is 0. And actually, we could talk about one of the properties you would have learned also that is being shown right here. If you have like a times b equals b times a, what is that property called where they switch the position, but the result is the same? Do you remember what it's called? This would be called the commutative property of multiplication because it just changed places. Okay, and your book would call it, what do they call it? The any order? Oh, they have a different name for it in your textbook. We'll find it later. I'm sure we'll come across it, but you learned it as the commutative property of multiplication. So theorem 2.2 is talking about the fact that the number 0 does not have a reciprocal. So I'm just reminding you right here, just two examples of what are reciprocals. If you have a number and you flip it over, that's the reciprocal. So 3 is the same thing as 3 divided by 1. So when you flip it over, you have 1/3. So a number and its reciprocal are the same sign. So they're either both positive or both negative. We're just taking the reciprocal, not the opposite sign reciprocal. More about that later on when we talk about perpendicular lines. So we have -5/2 and -2/5. Those are reciprocals of each other. Now 0 does not have a reciprocal itself because 0 is the same thing as 0 divided by 1, but when you flip this over, you would get 1/0, and you cannot divide by 0. That's undefined. So 0, the number 0 does not have a reciprocal. And then our last theorem right now is that for all real numbers, a and b, a minus b is the same thing as a plus the opposite of b. So subtraction is the same thing as adding the opposite sign. Okay, so we want you to look at what Sasha is doing right here. And by the way, this is your new textbook, Integrated Math 1, so Integrated Mathematics 1. It's the CME project. You may or may not have this textbook yet. School just started. No big deal if you don't have it yet, because anything you need, I will have for you in the files on Jupiter Grades. So you can pick up a book later if you don't have one yet. So for right now, in these integrated math books, so there's Integrated Math 1, 2, and 3. I teach Honors Math 1, and I teach both College Prep and Honors Math 3. But throughout these textbooks, you're going to see a lot of discussions between these characters in our books. And mostly it's Sasha and Tony. And then later on, you're introduced to somebody named Derman. So there's Sasha and Tony and Derman, and there may be one other one. I just can't remember off the top of my head, but Sasha and Tony come up over and over. So here's your first exposure to our character Sasha from from your textbook. She's trying to solve this equation right here, and she's using basic moves, so basic moves of algebra. So she just has rewritten the equation. She hasn't done anything yet. And then from this point to this point, what did she do? Can you tell what she did? Because everything on the left side is still the same. What has changed on the right side? She combined like terms. So on your paper, you have your paper handout of these notes that go along with this PowerPoint. You should be filling those in. If you are in class, you would have been handed those. And if you're not in class and you're doing this online from home, the file for this would be in Jupyter Grades also. You will have the PDF for the notes. So if you haven't printed them out yet, go do so right now. Pause this video and go do that, please. Otherwise, we're going to continue. And if you don't have a printer or you don't have ink, you can just write down what you see. So I would, on your notes right here, just write that she combined like terms, and you can even circle those two terms or underline them if you want to, because 2x plus 1x is 3x. So far, so good. She hasn't done anything wrong here. And then it looks like she's subtracting 3x from both sides of the equation because she's trying to move her term that has the x over here to the right side, or maybe she's moving it from the right side to the left side. We can't really tell that for sure because both sides of our equation have the same like terms. They are both 3x. So when you have this 3x minus this 3x, those are gone. That creates a zero pair. So they cancel each other out. And the same thing happened on the left side. So she's left with 2 equals 7. And there's a question mark above it, like, how can that be? Does 2 equal 7? No, it doesn't, obviously. So did she do something wrong, or what's going on here? Actually, Sasha didn't do anything wrong. This equation just doesn't have any solution. There is no number x such that when you multiply it by 3 and you add 2, it would equal the same thing as if you multiply it by 2, added another of that number, and then added 7. It's never going to equal that, because 3x plus 2 is never going to equal 3x plus 7, because this 3x would give you the same quantity on both sides, right? So there is no solution to that. She didn't do anything wrong. Let's look at number 2. What results do you get when you try to solve this equation here? So this involves something called the distributive property, where you need to distribute this number 4 to every term that's inside the parentheses. And terms are separated by pluses or minuses. So terms are things that are added or subtracted. So when you multiply 4 times x, you get 4x. And when you multiply 4 times 1, you get 4. So does the left side equal the right side? It does, doesn't it? You get 4x plus 4 does equal 4x plus 4. So in this case, there's no one answer for x. Actually, any number at all is going to work, all real numbers. And this is the symbol that I have right now on my computer. Later, when I see you or talk to you in a lesson next week, I will show you another way of handwriting that. But it kind of looks like the 2 parallel lines, the symbol for parallel lines, where there's just 2 slashes and then you just finish it off with like a capital R. So I will either write that on the board or I will show you online next time. But for now, that /R, it's a symbol that you can use instead of writing out the words all real numbers. We do it all the time in mathematics. We use that a lot instead of writing out the words. Okay, so when you are solving a linear equation, okay, there are 3 possibilities for an answer here, okay? And there's only 3 of them. You could have no solution like we had when Sasha was solving that equation. She got down to this point, right? Actually, she subtracted 3x from both sides and got 2 does not equal 7, but you can see from her next step that she had this. And so that has no solution. Another possibility is we have one and only one solution. It's a unique solution. So for example, if you solve this equation right now, what would you get? You can solve that right now on your paper. Go ahead and do that. Why don't you combine the x's to one side of your equation and your constant to the other side of the equation and finish solving it for x. What do you end up getting? 2x equals 16, therefore x equals 8. So 8 would be the one and only solution to this equation. The last possibility is there might be infinitely many solutions. There could be an infinite amount of them, meaning all real numbers, like that last example that we looked at. 4 times the quantity x plus 1 does in fact equal 4x plus 4. So that would have all real numbers as solutions. Okay, so I want you to pause this video right now, and I want you to work on these problems 3 through 7. Do the distributive property when you need it, and you should recognize when you're going to need it when you see a number in front of parentheses. And you should know that the operation means that you're going to multiply. So if you have a number factor out in front of a set of parentheses, you need to distribute that number or factor to each one of the terms inside the parentheses, and then combine your like terms. And here's where I would say, this is where I always see students making mistakes at the beginning of the school year. Typically, and I'm not saying all students make this mistake, but this is one that I see often. So I'm going to point it out to you so that hopefully you don't make this mistake. When you have like terms on one side of an equation, it's best to combine them on that side of the equation before moving it to the other side of the equation. Oftentimes I'll see students try to like move one constant number to the other side when there was another number on that same side of the equation that they could have combined it with. And same thing with your variable terms. And it's just actually a lot of times students make mistakes when they're doing that. They'll either make mistakes doing it, or it's just they're doing unnecessary steps. Okay, and so again, when I see you next week, I will show you some examples, and actually I will have some of your work already to grade so that I can find out if in fact any of my students are doing that now, and so that I can address that with you right away so that we can get you on the right track and so that you don't make those mistakes going forward. Okay, so you can work, you know, more efficiently. That's what our goal is, right? You're all going to be improving over this year. So if you haven't done so yet, I just kept rambling on, sorry. Go ahead and pause this video and solve all these, and then we're going to check your answers. So I am assuming at this point you are unpausing your video and you're checking your work. So let's look at this. When you were solving the equation in number 3 here, you would have gotten down to something like 10a minus 2 equals 10a plus 2, and that can't be. And if you actually subtracted out 10a from both sides, you would have gotten something like negative 2 equals 2. Well, that's obviously false. Negative 2 is not the same thing as positive 2, so that's why this is no solution. Number 4 is also no solution. You would have gotten something like 7 equals 5, and obviously they are not the same. Number 5 does have one unique solution, and actually solving it, you should have gotten 3 halves, which is the same thing as 1 1/2. And I love this because I can tell you right now, get used to having fractions as answers and not always using a calculator, okay? You could have put 1.5, but I would prefer you do this by hand, and you don't need a calculator for this one. This one was not difficult, okay? And I want you to know that a fraction that's improper, when you know what an improper fraction is, right? When the numerator is larger than the denominator, it's okay to leave your answer that way. You don't need to turn it into a mixed number as long as it's simplified, and this is simplified, okay? So we're going to be dealing with fractions a lot this year and going forward into your next classes, so get used to using your fractions in your work, okay? Number 6, your answer was all real numbers. You could have had that all real number sign, because this is true. When you distribute the 5 to the 2 minus k, you get the same thing as you do over here. Actually, yes, negative 5k plus 10 is the same thing as 10 minus 5k, right? Commutative property of addition, they just moved positions. And in the last example, this is no solution, because this would be equivalent to 3j plus 6. So 3j plus 6 is never going to be the same thing as 3j plus 2. So there you have it. Okay, our next section is 2.13, and we're going to focus on the distributive property. So before we get into that, I want you to work with somebody who's sitting next to you if you're in class. If you're at home doing this alone, I'm going to have you pause the video, and I want you to look at all three of these students' work, and only one of them is correct. I want you to figure out which one is correct, and the other two students have made mistakes, and they may have even made more than one mistake. So I want you to highlight those. I want you to point them out somehow, okay? So do that, work on that, either with a partner or by yourself. And then when you come back and unpause your video, you're gonna see my solutions here, and we'll talk about it. Okay, so the only one who was correct was Jenna. Jenna is the one that was correct. I need to move something out of my way here. Okay, so Rebecca, here's the error that Rebecca made. Hopefully you see that this was her mistake. She has a plus 12 here when it should be minus 12. Because Rebecca did distribute the 4 to not only the x, but also to the 3. But here's the mistake she made. She forgot it's negative 4 times positive 3 is negative 12. Because here it's correct. Negative 4 times positive x is negative 4x. Okay. But here was her mistake here. And then the other mistake I saw she made was she actually had a 57 right here. It's correct down here that it's 57, but up here she wrote 57 when she kind of like was already adding the 5 twice. So if you look at what happened between this step and the next step, was she was just adding 5 to both sides in order to move this negative 5 to the other side of the equation. And you could see in this format and in our other examples previously in these notes, when they're doing something, they're doing their what they call them, basic math moves. They're inverse operations, if you will, to move something from one side of the equation to the other. They're doing it in a horizontal format. You, like I, probably just do it vertically when we're writing these on our own paper, but they are showing them horizontally instead of vertically. So she was adding 5 here and she was adding 5 over here, but she actually added the 5 already when she wrote the 57. So that was a mistake. But down here it is correct because 52 plus 5 is 57. Okay. And so those were her mistakes right there, those two. Anna, on the other hand, she forgot entirely that she needed to distribute negative 4 to the positive 3. She just wrote down positive 3 again. And that is a common mistake I see students make. So don't be that student. Don't make that mistake. Remember, when there is a number in front of a set of parentheses, that means that number is a factor that needs to be distributed to every single term that you have in there, okay, in the parentheses. And you need to pay attention to the sign, like Rebecca forgot it over here for the second one. So it's negative 4 times x is negative 4x, and negative 4 times positive 3 is negative 12. And you can see that Jenna did them correctly down here. So the correct answer was 3. Jenna was the one that was correct. All right. Okay, what happened here? Sorry, guys, my video stopped. I'm going to pop. I don't know what the deal is when I'm recording on Zoom. Sometimes these PowerPoints of mine, they stop working when I click it. It doesn't go to the next slide. Okay. Another thing that they're going to talk about in this section is using expansion boxes. Okay, so expansion box, you might hear somebody call it a Punnett square. You deal with those in your science class. Other people will call it an area model. So for example, they're just using this model to show you how you can use it to find a product of numbers. Most often when we do this in our class here, we're going to be using it when we have expressions involving variables, like my very next example after this one. But they're just showing you, the reason why some people will call it an area model is it's because, like, if you had, treat this like a rectangle, like this was a rectangle right here. Okay, so if you have one side of your rectangle multiplied by the other side of your rectangle, like the length times the width, right? You would get the area of that rectangle. So the area is really the product of each one of these pieces, if you will, and these pieces are referring to the place value of the number. So if you say the number 327, that's 3 hundreds, you know, 2 tens or 20 and 7 ones. So you can split up a number into its place values and then distribute that other number, multiply it times each one of those. So 6 times 300 is 1800, and 6 times 20 is 120, and 6 times 7 is 42. So if you add all of these up now, that gives you the total product in there, which is 1962. Now that's just using numbers. As I mentioned before, a lot of times you can use this. It's really nice when we are using it to, you know, to multiply polynomials together. And I have an example at the very end of these notes, so I will talk about this some more then. But here's the same idea. If we put the 7, one of the factors that's being multiplied on one side, and each term of the other factor, so this makes up one factor and there's 2 terms in there, and you do need to put the negative sign with that if it's a negative. So just like we did up here, you multiply. So the 3x times the 7 is 21x, and 7 times -4 is -28. And therefore, so the answer to this, 3 times the quantity, 3x minus 4, is equal to 21x minus 28. You cannot combine those together because they are not like terms. We don't know what the variable x is. Okay, so we are going to use this a lot, or not a lot, but more in upcoming chapters, and then we definitely use it in our Math 3 class. Okay, so I want you to now just do some practice problems, okay? And some of these might be a little bit challenging, but that's okay. I have faith in you. I know you can do them. All right, and I want you to work on your own first. So if you are in class and you're, you know, sitting in there, obviously with other students, you may work together, but I want you to try them on your own first, okay? And then compare your strategies that you used and your solutions with your partner sitting next to you after you've given it a really good, honest effort to do it on your own, okay? So I want you to pause the video. Actually, I'm going to show you what they are before I show you answers. Let me take a peek. Yes. Okay, so I'm going to have you work on these. You're going to pause the video and you're going to work on them, okay? Because you have like 2 problems for each section that we've just talked about, okay? And they're dealing with equations here. So, and operations in the equations. Like, what are you going to do? You're multiplying, you're dividing, what are you doing? Okay, and I want you to know at first, there's multiple ways to do that number 9 right there. So pause your video and do that. Okay, I'm going to assume you've already been doing this and you want to check your answers now. So one of the ways you can approach this problem number 9 is, if you look right here, you have 10 times this quantity over here equals 90. So one thing you can do, yes, some of you might have actually distributed the 10 to both the 7a and the 5, and then, you know, you would have 50 right there and 70a, and then you would subtract 50 from both sides and then finish solving it for a. A lot of you might have done that, or some of you might have done that. But one of the things that you might have noticed is, what if you divided both sides by 10 first? If you divide both sides by 10, then you just get 7a plus 5 is equal to 9, okay? They want to know what 7a plus 15 is. We already have 7a plus 5. So what would we have to do next in order to make it 7a plus 15 instead of 7a plus 5? We'd need to add 10. If we added 10 here, I can't add 10 to 7a. They're not like terms. I don't know what a is. But if I could add 10 to the 5 and I could add 10 to the 9, because I have an equation, whatever I do on one side of my equation, I can do on the other side. And then this would give me my 15. I really don't need the parentheses at this point, so I'm going to drop them off. 7a plus 15 is equal to 19. So our answer was 19. And that's what you would have gotten if you accurately distributed the 10 and solved for the a. This one down here, Tony says, I'm thinking of a number. I do some things to it. So we don't know how many steps he does, but we know there's many steps here, multiple steps, I should say. And he ends up with 36 when he's all done. And he said, the very last 2 steps that I did was I added 11 and then I multiplied by 3. And then he got 36. So he did something to some number, and then he added 11, and then he multiplied that answer by 3, and he got 36. So he wants to know, what if everything that he did in the beginning was the same, but he changed these last 2 steps? What would his answer be? You can actually solve this. Think about it this way. Let's work our way backwards from what he said he did when he got 36. Okay? So let's reverse the last 2 things he did. Because when you're solving equations, like for example, right here, 10 times something equals 90. What did I do? I divided by 10. So if I knew my answer and that I had divided by 10, to get 9, what would I do to reverse that? I'd multiply by 10, right? So you do the inverse operation. So if his last 2 steps were he added 11 and then he multiplied by 3, so we got to reverse it in the reverse order also. So we'd have to take 36 and divide by 3 and then subtract 11. So that's what we're going to do here to figure out what his third to the last step was, because we still don't know what he did at the beginning. So in the last step, he got 36, and he got it because he multiplied by 3. So if we divide by 3, that means in the next to the last step, he had a 12. And he got that because he added 11 to some number. So that means if I reverse that and subtract 11, I get 1. Okay, so that means 1 must have been the third to the last step, whatever he did, Then this was the next to the last and second to last and then the last step, okay? So we know that we can start with 1 now and then just do these 2 things to it. And that's how you're going to get your answer. So now 1 plus 8. And if this isn't making sense, pause it, reverse this, back it up, listen to what I said again till it makes sense to you. So this was the third to the last step. And now we're going to add 8 to get 9. And then we're going to do the last step, multiply that by 8. And so our answer is 72. Did you get 72? Did you do that on your own? Kudos to you if you did. Good job. Okay, and then your other 2 problems that you were working on, you're solving this equation, and this means the opposite of everything inside the parentheses, so -1 times each of those. So we don't put the 1 there, but it's understood that that's a -1. So we're just taking the opposite sign. We're multiplying it by -1. So you get -s minus 2 equals 4s plus 1. So that would be your next step. And now we have s's on the left and s's on the right. We need to get the s's on one side, the constant on the other. You could actually add s to this side and get 5s and subtract 4 over here and get -6. Or you should get the same answer if you do that correctly. Or you could put your s's on the left by subtracting 4 s's and adding the 2 to both sides to get your constant on the right. And then the last step you're going to do is you're going to divide by -5. So your answer is S is -6/5. We're going to leave it like that. We're not using decimals, and I really don't need to say that it's -1 1/5. I can leave it as -6/5. That's fine. And lastly, they want you to know what's wrong here. Using an expansion box, show that the quantity a plus b squared is not necessarily equal to a squared plus b squared. Students will often make this mistake. Don't be that student. You can't do what I call shower the power here. You can't shower the power, meaning you cannot distribute an exponent to terms in parentheses here. You can distribute a power when you have nothing but a product in here, things being multiplied, or a quotient, things being divided, or both of those. It could be having things multiplied and divided in there, but no pluses or minuses in there. Okay, so it is not equivalent to a squared plus b squared. So I have 2 things that I'm about to show you. One, and your answer might vary if you're actually trying to plug in various numbers. So like if you're trying to come up with your own examples using a number for A and a number for B, there's multiple ways you can do this. This is just one idea coming up here, and here it is. If you let A and B both equal 1, look at what they're showing you would get. 1 plus 1 squared. Well, 1 plus 1, you do order of operations, right? You add the things in the parentheses first. That's 2. And 2 squared means 2 times 2, so that's 4. But what's a squared plus b squared? What is 1 squared? It's 1. And again, they were letting b equal 1 here, so you have another 1 squared, that's 2. And obviously, 4 does not equal 2. So this is one counter example that's using a specific example when we have something that is only in variable. They're only variables, okay? They're not giving us actual numbers. But here's me about to show you the expansion box. So here's how you can set up an expansion box. You don't really need this space here, but I had to use a table to do this. So if I want the quantity a plus b squared, it means I have one side. Think of it like a square, because isn't a square just one side squared? So a square instead of a rectangle. So I have my a plus my b. Now, if this was a minus in here, I'd have a negative with the b in both spots. But I'm taking whatever I have and I'm multiplying it by itself. So I have the same side here, the same side over here. So a plus b, positive a, positive b, positive a, positive b. So here's my expansion box. Again, it's the product. You always multiply these. So you're always multiplying the row and the column, and the product goes in that cell. And this is called a cell and another cell. So this is why some people will call it the area model. So a times a is a squared. You're not adding them, you're multiplying them. A times a is a squared. It's not 2a. And a times b is just ab. I don't know what a is and I don't know what b is. And b times a, I could have written b times a. I could have written ba. But ba and ab are the same thing. Commutative property, we can move things around. And then b times b, so where that row meets that column, b times b is b squared. So now I've got these 4 terms. It's a squared plus ab plus another ab plus b squared. And these are the only 2 like terms that I can add together because they're the exact same variable with the exact same exponent. They just have an exponent of 1. We don't need to write it. So the quantity a plus b squared is equal to a squared plus 2ab plus b squared. Do you see how it's not? You can't just go, oh, I can shower this power. It's a squared plus b squared. No, you can't do that because these are terms in here. They have a plus. And if this had been a minus instead, our answer would have been a squared minus 2ab plus b squared, because a negative times a negative would be positive. So these both would be positive, but these would be negatives. So you'd have -2 of them. Okay, there you have it.